Right now, as you watch this video, a beam of light is traveling from your screen to your eyes at exactly 299,792,458 meters per second. This number is not approximate. It is not rounded. It is the most precisely measured constant in the entire universe. And it is the wall that separates you from everything you will never touch. Consider this carefully. The nearest star beyond our Sun, Proxima Centauri, floats just 4.24 light-years away. That sounds almost manageable, does it not? A mere cosmic neighbor. But here is what that distance actually means. If you could somehow accelerate a spacecraft to 1% of the speed of light, an engineering miracle beyond anything we have ever built, you would still need 424 years to reach it. Generations of humans would be born, live, and die inside that metal cocoon. And Proxima Centauri is the closest star. What about the Andromeda Galaxy, our nearest major galactic neighbor? 2.5 million light-years. Even traveling at 99.9% of light speed, a velocity that would require more energy than humanity has produced in its entire history, you would need over 2,500 years to arrive. The passengers who departed would share nothing with those who arrived, except perhaps some fragments of genetic code. But here is what makes this truly terrifying. The speed of light is not merely a technical limitation. It is not like the sound barrier, which we broke with enough engineering cleverness. The speed of light is woven into the very fabric of reality itself. It is the rate at which causality propagates through the universe. It is the speed at which time becomes space and space becomes time. And no amount of genius, no technological revolution, no breakthrough in physics will ever change it. What does this mean for us? What does it mean for our dreams of cosmic exploration, for our hope of finding others in this vast darkness? Are we truly alone, not by cosmic accident, but by cosmic design? Today, we will travel from the equations of Albert Einstein to the edge of the observable universe. We will examine experiments that have tested light speed to 20 decimal places and found no deviation whatsoever. We will explore what happens when you approach this cosmic speed limit and why time itself conspires to keep you imprisoned. And by the end, you will understand something profound about your place in this universe, something that is simultaneously devastating and strangely beautiful. Let us begin with something deceptively simple. What is light exactly? In 1864, a Scottish physicist named James Clerk Maxwell was sitting in his study at King's College London. He had been working for years on the relationship between electricity and magnetism. Other scientists had established that moving electric charges create magnetic fields. They had shown that changing magnetic fields create electric currents. But Maxwell saw something no one else had seen. He wrote down 4 equations, just 4 elegant mathematical statements that unified electricity and magnetism into a single phenomenon. But when he solved these equations, something unexpected emerged. They predicted the existence of waves, electromagnetic waves that would propagate through space at a specific velocity. Maxwell calculated this velocity from pure theory. The answer was approximately 300,000 kilometers per second. He stared at this number. It was almost exactly the measured speed of light. This was not a coincidence. Maxwell had just discovered that light itself is an electromagnetic wave. Visible light, radio waves, X-rays, gamma rays, all the same fundamental phenomenon vibrating at different frequencies, and all of them traveling at exactly the same speed through empty space. But here is what puzzled physicists for decades. Waves need a medium. Sound waves travel through air. Ocean waves travel through water. What medium does light travel through? The answer, discovered through decades of failed experiments, is nothing. Light does not need a medium. It propagates through pure vacuum. And its speed is not relative to any physical substance. It is absolute. In 1887, two American physicists named Albert Michelson and Edward Morley attempted to measure Earth's motion through the supposed luminiferous ether, the hypothetical medium that everyone assumed light must travel through. Their experiment was elegant. They split a beam of light into two perpendicular paths. One path aligned with Earth's orbital motion around the Sun. The other path was perpendicular to it. If Earth was moving through an ether, light traveling along the direction of motion should be slightly slowed compared to light traveling perpendicular to it. They built their interferometer on a massive sandstone slab floating in a pool of mercury to eliminate vibrations. They repeated the measurements over months, at different times of day, at different seasons. The precision of their instrument could detect velocity differences as small as a few kilometers per second. The result was null. Completely, absolutely null. No matter which direction they pointed their apparatus, no matter what time of year they measured, the speed of light remained stubbornly constant. Earth's velocity through space, roughly 30 kilometers per second in its orbit around the Sun, produced no detectable effect whatsoever. This was a crisis. Either the ether existed and had some bizarre property that perfectly concealed Earth's motion, or something fundamental was wrong with the entire framework of classical physics. For 18 years, this puzzle remained unsolved, until a 26-year-old patent clerk in Bern, Switzerland, published a paper that would shatter our understanding of space and time forever. Albert Einstein in 1905 did not have access to a university laboratory. He did not have colleagues to discuss his ideas with. What he had was an extraordinary ability to take a physical principle seriously, more seriously than anyone else had been willing to take it. Einstein asked a simple question. What if the speed of light is truly constant? Not approximately constant, not constant in most circumstances, but absolutely, fundamentally, inviolably constant for all observers in all situations. If you are standing still and measure the speed of a beam of light, you get c. If you are moving at half the speed of light toward the source and measure the same beam, you still get c. If you are moving at 99% of the speed of light away from the source, you still measure exactly c. This seems impossible. In everyday experience, velocities add. If you are on a train moving at 100 kilometers per hour and throw a ball forward at 20 kilometers per hour, the ball moves at 120 kilometers per hour relative to the ground. But light does not work this way. Einstein realized that if the speed of light is truly constant, then something else must be variable. And the only things left to vary are space and time themselves. What followed was special relativity. The word special does not mean exceptional. It means restricted, limited to the special case of uniform motion. But its implications were revolutionary. Time is not universal. Two observers moving relative to each other will disagree about how much time has passed between events. Space is not universal. They will disagree about distances between objects. And these disagreements are not errors or illusions. Both observers are equally correct. The faster you move relative to something, the more your measurements of time and space differ from theirs. And as you approach the speed of light, these differences become extreme. Here is where the prison walls become visible. Imagine you have a spacecraft capable of tremendous acceleration. You fire the engines and start moving faster and faster. At low speeds, everything seems normal. You accelerate. Your velocity increases. You keep accelerating. Your velocity keeps increasing. But as you approach the speed of light, something strange happens. You feel the engines pushing. You measure your acceleration as constant. But observers watching you from Earth see your acceleration diminishing. Your velocity asymptotically approaches c, but never quite reaches it. Why? Because of the relationship between energy and mass. Einstein showed that mass and energy are equivalent. His famous equation, E equals mc squared, expresses this equivalence. But there is another equation from special relativity that is equally important. As your velocity increases, your relativistic mass increases according to the Lorentz factor. At 50% of light speed, your mass has increased by about 15%. At 90% of light speed, your mass has more than doubled. At 99%, your mass is over 7 times its rest value. At 99.9%, over 22 times. At 99.99%, over 70 times. The energy required to accelerate an object scales with its mass. So, as you approach c, the energy required to accelerate you further grows without limit. To actually reach the speed of light, you would need infinite energy. This is not a technological limitation. It is not about building better engines or finding more powerful fuel sources. It is a fundamental mathematical consequence of the structure of space-time itself. The speed of light is a hard boundary written into the equations that govern reality. But wait, you might say, what about time dilation? If time slows down for a fast-moving traveler, could they not reach distant stars within their own lifetime, even if millennia pass on Earth? This is correct, and it makes the situation both better and worse. Let us calculate precisely. Suppose you board a spacecraft that can maintain a constant acceleration of 1 g, approximately 10 meters per second squared. This is comfortable for human passengers and represents a plausible advanced technology. After 1 year of proper time, the time you experience on the ship, you would be traveling at about 77% of light speed. After 2 years, 97%. After 3 years, 99.5%. After 4 years, 99.9%. With constant 1 g acceleration for the first half of your journey and constant 1 g deceleration for the second half, you could reach Proxima Centauri in about 3.5 years of your time. The Andromeda Galaxy, 2.5 million light-years away, in about 28 years of your time. Sounds almost reasonable, does it not? 28 years to another galaxy. A long voyage, but not an impossible one. But here is the devastating reality. While you experience 28 years, Earth experiences over 2.5 million years. When you arrive at Andromeda and look back, the Sun has become a white dwarf. Humanity is either extinct, unrecognizably evolved, or has spread across the galaxy. Everything you knew is dust. And you can never go back. Not really. You can make the return journey, another 28 subjective years, but you would arrive more than 5 million years after you left. You would not return to your time. You would emerge into an utterly alien future. Time dilation does not free you from the prison. It simply allows you to pace your cell more efficiently while the universe ages around you. Perhaps you are thinking about wormholes. Surely science fiction has offered us an escape route. In 1935, Einstein himself, working with Nathan Rosen, described a theoretical structure now called an Einstein-Rosen bridge. This is a shortcut through space-time, connecting two distant points, as if folding a piece of paper and pushing a pencil through. The mathematics of general relativity permits such structures. They are solutions to Einstein's field equations. But the same mathematics reveals devastating problems. First, naturally occurring wormholes, if they exist at all, would be microscopic. We are talking about sizes comparable to the Planck length, roughly 10 to the negative 35 meters. About 20 orders of magnitude smaller than a proton. No human, no spacecraft, no atom could possibly pass through. Second, to create a traversable wormhole large enough for a spacecraft, you would need what physicists call exotic matter. This is not antimatter, which we can produce in tiny quantities. Exotic matter has negative energy density. It violates the weak energy condition, one of the fundamental assumptions of general relativity. Does exotic matter exist? Perhaps. Quantum effects near black hole horizons might produce something like it. But the quantities required to hold open a human-scale wormhole are astronomical. Physicists like Kip Thorne at the California Institute of Technology have calculated that stabilizing a 1-meter wormhole would require about a Jupiter mass of exotic matter. And even if you could collect this impossible substance, Wormholes may be inherently unstable. The slightest perturbation, including the passage of a spacecraft, might cause them to collapse into black holes. There is also the causality problem. A traversable wormhole can theoretically be converted into a time machine. You could send information back to your own past. This creates logical paradoxes that physicists deeply distrust. Most researchers believe that some as-yet undiscovered principle of physics forbids stable traversable wormholes. Stephen Hawking called this the chronology protection conjecture. The universe seems to conspire to prevent violations of causality. Wormholes are not your escape route from the prison. They are more likely theoretical curiosities that nature prohibits in practice. What about Alcubierre warp drive? This sounds genuinely promising. In 1994, Mexican physicist Miguel Alcubierre published a remarkable paper. He showed that general relativity permits a configuration of spacetime where a bubble of flat space moves faster than light through the surrounding spacetime. The bubble itself does not exceed the local speed of light. Instead, spacetime in front of the bubble contracts, while spacetime behind it expands. The spacecraft inside the bubble remains stationary relative to its local space, but the bubble carries it across the universe at arbitrary velocities. This is not faster than light travel in the conventional sense. Nothing inside the bubble moves faster than c. It is more like standing on a surfboard while the ocean itself moves beneath you. Beautiful, elegant, tantalizing, and almost certainly impossible. The energy requirements are the first problem. Alcubierre's original calculations suggested you would need the mass energy of a Jupiter-sized planet, converted entirely into exotic matter. Later refinements by physicists like Harold White at NASA reduced this estimate to perhaps the mass energy of Voyager 1. Still enormous, but conceivably achievable by an advanced civilization. But the exotic matter problem returns with a vengeance. The Alcubierre drive requires negative energy density in very specific configurations. This is the same exotic matter that wormholes require, and we have no evidence it can exist in macroscopic quantities. There are also fundamental problems with how the drive would actually work. Who controls it? The bubble creates a region causally disconnected from the outside universe. The pilot inside cannot send signals to the bubble wall to steer or stop the drive. How do you turn it off? When the bubble decelerates, it releases accumulated radiation at tremendous energy levels. The Alcubierre drive would arrive at its destination preceded by a blast of particles energetic enough to sterilize entire solar systems. And recent work by physicists at the University of Sydney suggests that the quantum effects within the bubble might be inherently unstable. The drive might not just be difficult to build, it might be impossible, even in principle. Let us step back and consider what we have learned. The speed of light is constant because it is built into the geometry of spacetime. It is not a speed limit in the conventional sense, like a highway maximum. It is more like the relationship between north and east. You cannot go more than north. The question does not even make sense. Every proposed faster-than-light technology either requires substances that probably cannot exist, creates paradoxes that physics seems to forbid, or has subtle flaws that make it unworkable. But this leads to a profound philosophical question. Why? Why is the universe structured this way? Is there a purpose to our imprisonment? Some physicists have speculated that the light speed barrier serves a function. It may prevent causality violations that would create logical inconsistencies in the universe. It may be necessary for thermodynamics to work correctly, for entropy to increase, for time to have a direction. Others have suggested anthropic explanations. Perhaps only universes with this structure can produce complex observers. Perhaps the speed of light must be what it is for stars to form, for chemistry to work, for life to evolve. But these explanations, however satisfying intellectually, do not change our situation. We remain confined. Let us now confront the true scale of our isolation. The observable universe has a radius of about 46.5 billion light-years. This is larger than its age of 13.8 billion years would suggest, because space itself has been expanding. Light that left distant objects billions of years ago has been stretched by cosmic expansion, and the sources that emitted that light have been carried even farther away. Beyond the observable universe, space almost certainly continues. Our best models suggest the cosmos is either infinite or enormously larger than what we can see. And all of it is inaccessible. In fact, due to cosmic expansion, most of the observable universe is already causally disconnected from us. Galaxies more than about 14 billion light-years away are receding faster than light. Not because they are moving through space faster than c, which is forbidden, but because the space between us and them is expanding so rapidly. These galaxies are visible only because their ancient light, emitted billions of years ago when they were closer, is still reaching us. But we could never visit them. We could never even send them a message that would arrive. They are lost to us forever. And the situation is getting worse. As the universe continues to expand, more and more galaxies cross this cosmic event horizon, vanishing from our potential future light cone. In about 100 billion years, observers in our galaxy will see nothing but the merged remnants of our local group. The rest of the cosmos will have disappeared beyond the horizon. The prison walls are not just impassable, they are closing in. Does this mean we are alone? This question has haunted humanity since we first understood the scale of the cosmos. If civilizations cannot cross interstellar distances, if every intelligent species is confined to its own tiny corner of the universe, then we might exist in a cosmos teeming with life but utterly silent. The physicist Enrico Fermi famously asked, "Where is everybody?" If the universe is billions of years old and contains billions of potentially habitable planets, surely someone should have colonized the galaxy by now, even at sublight speeds. But the speed of light constraint offers one possible answer. Perhaps civilizations arise, look at the distances involved, and simply stay home. Think about what interstellar colonization would actually require. Journeys lasting centuries or millennia. Generation ships, where the travelers who arrive are many generations removed from those who departed. Or suspended animation technologies that border on resurrection from death. Or machine intelligences that care nothing about the passage of time. Perhaps civilizations that achieve this capability lose interest in biological expansion. Perhaps they turn inward, building simulated universes more interesting than the physical cosmos. Perhaps they transcend in ways we cannot comprehend. Or perhaps they simply accept their confinement, as we may eventually have to accept ours. But here is where the story takes an unexpected turn. Perhaps confinement is not the tragedy we imagine. Consider what we know about the universe. There are roughly 200 billion to 2 trillion galaxies in the observable cosmos. Each contains between 100 million and 1 trillion stars. Around these stars orbit planets, some of which may harbor life, some of which may develop intelligence. If life is common, if intelligence is not extraordinarily rare, then the universe may contain billions of civilizations. Each one confined to its own stellar neighborhood, each one looking out at the same unreachable stars, each one asking the same questions we ask, and none of them able to conquer or consume the others. The light-speed prison may be the reason the universe is not already dominated by some ancient, aggressive species that arose billions of years before us. It may be the reason there is room for new civilizations to emerge, grow, and develop their own unique perspectives on existence. The prison may be a sanctuary. There is something else to consider. The speed of light is incredibly fast by human standards. Light travels from the Earth to the Moon in about 1.3 seconds. To Mars, at closest approach, about 3 minutes. To the outer planets, a few hours. To the edge of the solar system, roughly a day. Within our own solar system, the light speed constraint is an engineering challenge, not a fundamental barrier. We could potentially establish colonies throughout our cosmic backyard, from Mercury to the Kuiper Belt, with communication delays measured in minutes to hours. A solar system civilization would be vast, diverse, and capable of extraordinary achievements. And our solar system is not small. The Oort cloud, the shell of icy bodies surrounding the Sun, extends perhaps 2 light-years from us. This is a volume of space roughly the size of a sphere, containing dozens of neighboring star systems. It may contain trillions of comets and minor planets. Resources enough for millions of human civilizations. What if we reframe our perspective? What if we stop mourning the stars we cannot reach and appreciate the vastness we can access? There is also the question of time. Humanity has existed for roughly 300,000 years. Civilization for perhaps 10,000 years. Industrial technology for 200 years. Spaceflight for 65 years. The Sun will continue shining for another 5 billion years. Even in its current stable state, it will warm the Earth for perhaps 1 billion more years before becoming too luminous for comfort. After that, Mars becomes more habitable as Earth becomes less so. The outer solar system moons become temperate as the Sun expands. We have time. Vast, almost inconceivable amounts of time. Even at the glacial pace of chemical rockets, which can achieve perhaps 20 kilometers per second, our descendants could reach the nearest stars in tens of thousands of years. This is longer than human civilization has existed, but it is a blink compared to the future available to us. And technologies improve. Nuclear pulse propulsion, like the Orion project studied in the 1960s, could reach a few percent of light speed. Laser-pushed light sails, like the Breakthrough Starshot project, might achieve 20%. Even without exotic physics, even respecting the light speed barrier absolutely, we could slowly, generationally, eventually spread through the galaxy. It would take millions of years, tens of millions. But the Sun gives us billions. The mathematician and philosopher Blaise Pascal once wrote about human insignificance. He described humanity as a thinking reed, fragile and temporary, lost in the infinite spaces of the cosmos. But he also noted that the universe does not know it crushes us, while we know that we die. Our awareness, our capacity to understand our situation, gives us a dignity the blind universe cannot possess. I want to propose something similar about our cosmic imprisonment. Yes, we are confined. The stars will always be almost unreachably distant. The galaxies beyond our local group will disappear forever. The universe is structured in a way that isolates each intelligent species in its own small region of space and time. But we can understand this confinement. We can describe it precisely with mathematics. We can measure the speed of our prison walls to 20 decimal places. We can contemplate what lies beyond even if we cannot visit it. And perhaps that is enough. Perhaps understanding is its own form of transcendence. In 1990, the Voyager 1 spacecraft was about 6 billion kilometers from Earth, beyond the orbit of Neptune, heading for interstellar space. At the request of astronomer Carl Sagan, NASA commanded the probe to turn its camera back toward the inner solar system and take a final photograph. The resulting image shows Earth as a single pale blue pixel suspended in a ray of scattered sunlight, a mote of dust in a vast cosmic beam. Sagan wrote about this image with characteristic eloquence. He observed that everyone you have ever heard of, every human being who ever was, lived out their lives on this tiny speck. All our wars, our religions, our civilizations, our triumphs and tragedies occurred on this barely visible point in the blackness. But he did not see this as cause for despair. He saw it as reason for humility, for compassion, for taking care of the only home we have ever known. I suggest we apply similar thinking to our cosmic imprisonment. The speed of light is a prison. This is scientifically accurate. We cannot escape it. We will never travel to Andromeda in person. We will never see what lies beyond the cosmic horizon. We are confined to a small region of an enormous universe, and that region will only get smaller as cosmic expansion continues. But consider what exists within our prison. A sun that will burn for billions more years. Planets and moons with more land area than we could explore in a million lifetimes. Asteroids and comets containing more resources than we could ever exhaust. And on our tiny blue world, billions of human beings, each with their own consciousness, their own experiences, their own capacity for wonder. The atoms in your body were forged in the cores of ancient stars. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was synthesized in stellar furnaces and scattered across space when those stars exploded. You are literally made of star stuff, a portion of the universe that has become conscious and is now contemplating its own existence. Is that not remarkable enough? Do we need to reach the unreachable to find meaning? Here is what I want you to understand. The speed of light is not a cruelty imposed upon us. It is a feature of reality that makes reality possible. Without it, causality breaks down. Without causality, there can be no physics, no chemistry, no biology, no you. The prison walls are made of the same laws that allow you to exist. And within those walls, there is more than enough space, more than enough time, more than enough mystery to occupy any civilization for any duration. We have not explored our own ocean floors. We have not cataloged all the species on our own planet. We have not understood our own consciousness. We have not even fully mapped the solar system we were born into. The universe has given us a gift so large we cannot see its edges. And we sit here, complaining that there are edges at all. But let me address the dreamers, those who refuse to accept limitations, who believe that every barrier eventually falls to human ingenuity. I respect this attitude. It has driven our species to remarkable achievements. The sound barrier was once considered unbreakable, and now commercial aircraft routinely exceed it. Space was once the realm of gods, and now we have footprints on the moon. Perhaps there is physics we do not yet understand. Perhaps the universe contains loopholes we have not discovered. Perhaps some future Einstein will find a way around the light-speed barrier that we cannot currently imagine. I cannot prove this impossible. I can only say that the evidence points overwhelmingly against it. The speed of light has been tested in every conceivable way for over a century. It has been measured in vacuum and in materials. It has been probed with photons and electrons and neutrinos. It has been confirmed by GPS satellites and particle accelerators and astronomical observations. Every single measurement agrees. The speed of light is constant to within 1 part in a billion billion. There are no hints of deviations, no anomalies that suggest hidden structure. If there is a loophole, nature has hidden it extraordinarily well. And even if a loophole exists, even if future physics permits faster than light travel, will it change the fundamental situation? Consider wormholes that work. Consider warp drives that function. What happens when civilizations can cross the galaxy in days or weeks instead of millennia? The optimistic answer is that we finally meet our cosmic neighbors, exchange knowledge and culture, join a galactic community. The pessimistic answer is that interstellar war becomes possible. The same technologies that would let us reach the stars would let hostile species reach us. The prison walls may be protection as much as confinement. Or perhaps civilizations that develop such technologies rapidly destroy themselves with them. Perhaps the light-speed barrier is a filter that prevents cosmic catastrophe. We do not know. We cannot know until we understand far more about both physics and the sociology of intelligence than we currently do. What we can know is our present situation. We are a young species on a small planet orbiting an ordinary star in the suburbs of an unremarkable galaxy. We have developed technology that lets us see the universe clearly, but not technology that lets us traverse it quickly. We will likely spend millennia, perhaps millions of years, confined to our solar system, or at most, our immediate stellar neighborhood. Our descendants may eventually colonize the galaxy, but they will do so slowly, generationally, in a great migration lasting longer than recorded history. And throughout this entire journey, the speed of light will remain constant. The barrier will remain firm. The universe will remain vast beyond our reach. This is reality. This is the situation we must make peace with. But making peace does not mean accepting despair. It means finding meaning within constraints. Every human life is constrained. We are confined to one body, one perspective, one brief span of years. We cannot experience the thoughts of others directly. We cannot visit the past or preview the future. We are prisoners of the present moment. And yet, within these constraints, we find love and purpose and beauty. We create art and science and civilization. We connect with each other despite our isolation. We build meaning from finite materials. Why should cosmic constraints be any different? Yes, we cannot reach Andromeda, but we can photograph it. We can analyze its light and understand its composition. We can calculate its trajectory and predict its collision with our own galaxy in 4 billion years. We can know it even if we cannot visit it. Knowledge is a form of presence. Understanding is a form of connection. The mind can travel where the body cannot. In the end, what is the speed of light but information? What is c but the rate at which the universe tells itself what is happening? Light carries information from the sun to your eyes. It carries information from distant galaxies to our telescopes. It carries the state of reality from one place to another at the fastest possible rate. We are information processors. Our brains extract patterns from sensory data and construct models of reality. Our civilization extends this process with instruments that see what eyes cannot, and with mathematics that describes what instruments cannot measure. The speed of light limits the physical transfer of matter. It does not limit the growth of understanding. Our knowledge of the cosmos expands far faster than any spacecraft could travel. In one sense, we have already escaped the prison. Our minds have reached the cosmic microwave background, the edge of the observable universe, the beginning of time itself. We understand physical processes that occur in the cores of neutron stars and in the hearts of black holes. We can describe the first moments after the Big Bang and predict the ultimate fate of matter. The prison walls contain our bodies. They have never contained our thoughts. So what should we do with this understanding? First, appreciate what we have. The Earth is a paradise by cosmic standards. Liquid water, breathable atmosphere, moderate temperatures, abundant resources. Most of the universe is vacuum or plasma or frozen rock. We won the cosmic lottery simply by existing here. Second, preserve what we have. Our planet is fragile. Human civilization depends on stable climate, functioning ecosystems, and social cooperation. These are not guaranteed. We could easily destroy ourselves long before cosmic distances become relevant. Third, explore what we can. The solar system awaits. Mars and the moons of Jupiter and Saturn offer genuine frontiers. The asteroids contain wealth beyond calculation. A mature solar system civilization would be wondrous beyond our current imagination. Fourth, keep looking outward. Even if we cannot visit the stars, we can study them. We can search for life on other worlds. We can listen for signals from other civilizations. We can try to understand our place in the cosmic order. And fifth, accept our limitations with grace. The universe is not obligated to be convenient. Reality is what it is, not what we wish it were. Maturity means working within constraints rather than raging against them. Let me leave you with a final thought. The speed of light is 299,792,458 meters per second. This number will not change. It will not bend to human ambition or technological progress or desperate need. For as long as the universe exists, for as long as physics operates as we understand it, this will be the cosmic speed limit. Every intelligent species that ever arises, in every galaxy, in every era, will eventually discover the same barrier and face the same isolation. We are not uniquely cursed. We are simply aware of the universal condition. And in that awareness, there is a strange comfort. Somewhere out there, perhaps around a star whose light has not yet reached us, another conscious being is looking at the same unreachable sky and asking the same unanswerable questions. We are alone together, separated by light years we cannot cross, but united in our contemplation of the vast and beautiful prison we share. The speed of light is a wall, but it is the same wall for everyone, and perhaps that is the closest thing to cosmic community we will ever know. Part 2. The Mathematics of Imprisonment. Now that we have understood the emotional and philosophical weight of our situation, let us examine precisely how this prison is constructed. The mathematics of special relativity is not merely abstract. It is the blueprint of our confinement. In 1873, Dutch physicist Hendrik Lorentz was studying Maxwell's equations of electromagnetism. He noticed something peculiar. The equations contained a factor that became important at high velocities. This factor, which we now call the Lorentz factor, is represented by the Greek letter gamma. The formula is deceptively simple. Gamma equals 1 divided by the square root of 1 minus v squared over c squared. Here, v is your velocity, and c is the speed of light. Let us explore what this equation actually means for your freedom of movement. At zero velocity, gamma equals exactly 1. Nothing unusual happens. Time flows normally, distances are unchanged, mass is what your scale reads. At 10% of light speed, gamma is approximately 1.005, a 5% correction, barely noticeable. At 50% of light speed, gamma is approximately 1.15. Now time dilates by 15%. A year on your ship corresponds to about 11.5 months on Earth. At 90% of light speed, gamma exceeds 2.2. Time moves more than twice as slowly for you compared to external observers. Distances in your direction of travel contract to less than half their rest length. At 99%, gamma exceeds 7. At 99.9%, it exceeds 22. At 99.99%, it exceeds 70. And as v approaches c, gamma approaches infinity. This is not metaphorical. It is not approximate. The Lorentz factor is the precise mathematical description of how space-time warps around a moving object. What does infinite gamma mean? It means that at the speed of light, time stops completely. A photon experiences no passage of time whatsoever. From the photon's perspective, if we can even speak of such a thing, emission and absorption are simultaneous, regardless of the distance traveled. It means that at the speed of light, distances in the direction of motion contract to zero. The photon does not travel through space in any meaningful sense. Space itself collapses along its path. And it means that the energy required to accelerate any massive object to the speed of light is infinite. Not very large, not astronomical, mathematically infinite. This is the hard boundary. This is where the equations say, quote, zero. Let us calculate specific energy requirements to understand just how hard this boundary is. The relativistic kinetic energy of an object is given by gamma minus 1 times its rest mass times c squared. At low speeds, this reduces to the familiar half mv squared from high school physics. But at high speeds, the gamma factor dominates. Consider a 1 kilogram object. At 10% of light speed, its kinetic energy is about 450 terajoules. This is roughly the energy released by a 100 megaton nuclear bomb, the largest ever designed. At 50% of light speed, the energy is about 1.7 times 10 to the 16th joules, about 4,000 times more, comparable to the annual energy consumption of a medium-sized country. At 90% of light speed, approximately 3.1 times 10 to the 17th joules, a significant fraction of the world's total annual energy production. At 99%, about 1.4 times 10 to the 18th joules. More energy than human civilization produces in several years. At 99.9%, about 4.4 times 10 to the 18th joules. You could power human civilization for decades on this energy. And the closer you get to C, the worse it becomes. Each additional 9 in the velocity requires roughly another order of magnitude more energy. The barrier is not just difficult, it is exponentially, impossibly, irrevocably difficult. But perhaps you are thinking that we could gather enough energy if we tried hard enough. After all, the sun produces about 4 times 10 to the 26 watts. Over the course of a year, that is roughly 10 to the 34 joules. Surely, a sufficiently advanced civilization could harness enough solar energy? Let us imagine such a civilization. They have constructed a Dyson sphere, a shell surrounding their star to capture all its output. They have accumulated energy for centuries. They decide to accelerate a single human being, mass approximately 70 kilograms, to 99.9% of light speed. The energy required is about 3 times 10 to the 20 joules. If they could convert solar energy with perfect efficiency and had storage systems that lost nothing, they would need to collect the sun's entire output for about 100 seconds. This sounds almost feasible for a Dyson civilization, but remember, they have accelerated only one person. To accelerate a 1,000-person generation ship with all its life support and fuel and structure, perhaps 1,000,000 metric tons, requires 1,000,000 times more energy. Now they need the sun's output for over 3 years, and 99.9% is not enough to make interstellar distances tractable within a human lifetime. Even at this velocity, the subjective time to reach Proxima Centauri is about 2 years, but the Andromeda Galaxy still requires over 1,000 years of subjective time. To reduce the Andromeda journey to a human lifetime, you need to get much closer to C. At 99.9999%, Gamma exceeds 700. The subjective journey time drops to about 35 centuries divided by 700, or about 5 years. But the energy requirements at 99.9999% are roughly 100 times greater than at 99.9%. Now, your Dyson civilization needs to harvest the sun for 300 years to accelerate a single ship. And at the destination, you must decelerate. That requires the same amount of energy again. So, 600 years of stellar energy collection for one round trip. This is for a single ship. A civilization that wanted to colonize Andromeda in any meaningful sense would need thousands or millions of ships. The energy requirements become genuinely astronomical, requiring stellar engineering on scales we can barely imagine. There is another approach. Rather than accelerating a massive ship, what if we could send information instead? Light itself travels at c. We could, in principle, transmit the complete information content of a human being, their neural structure, their memories, their personality, as a radio signal. At the destination, sophisticated technology could reconstruct the person from this information. This is not as far-fetched as it might sound. We are already developing technologies to map brain structure at increasing resolution. Information can be encoded in electromagnetic radiation and transmitted at light speed. If consciousness is ultimately computational, as many neuroscientists believe, then it might be transferable. But notice what has happened. We have not escaped the prison. We have merely found a way to pace our cell at maximum efficiency. The information still travels at c, no faster. A transmission to Andromeda still takes 2.5 million years. The original person has died long before the reconstruction exists. Is the reconstruction the same person? This is the ancient philosophical puzzle of personal identity. If your exact atomic structure is copied, is the copy you? Most people have strong intuitions that it is not. You want continuity of experience, not duplication. Even if we accept transmission and reconstruction as legitimate travel, we remain bound by C. The universe has not granted us an escape. it has merely offered a more efficient form of imprisonment. Let us return to the physics and examine why C is special. In 1905, when Einstein formulated special relativity, he made two postulates. First, the laws of physics are the same for all observers in uniform motion. Second, the speed of light in vacuum is the same for all observers, regardless of their motion or the motion of the source. From these two postulates, the entire edifice of special relativity follows. Time dilation, length contraction, mass-energy equivalence, the impossibility of faster-than-light travel. All of it derives from the constancy of C. But why is C constant? What makes light special? The answer has nothing to do with light itself. Light just happens to be the most familiar phenomenon that travels at this speed. The deeper truth is that C is the speed of causality. In relativity, we learn that space and time are not separate. They are woven together into a four-dimensional fabric called spacetime. Events that seem simultaneous to one observer may not be simultaneous to another. The order of events can differ depending on your frame of reference. But this does not mean everything is relative. There is an invariant structure to spacetime, defined by the light cones. From any event, you can draw a cone into the future representing all locations that could be affected by that event. This is the future light cone. You can also draw a cone into the past representing all locations that could have influenced that event. This is the past light cone. Events inside your future light cone can be reached. Events outside cannot be reached, ever, by any means. Events inside your past light cone could have affected you. Events outside your past light cone could not have affected you in any way. This structure is absolute. It does not depend on your velocity or reference frame. The light cones define the causal structure of the universe, the pattern of what can influence what. And the boundaries of these cones, the surface where inside meets outside, are defined by the speed of light. C is not merely the speed at which light happens to travel. It is the speed at which causality propagates. It is the rate at which the future emerges from the present. This is why faster-than-light travel is not merely difficult, but conceptually problematic. If you could travel faster than light, you could exit your future light cone. You could reach events that are causally disconnected from your departure. From some reference frames, you would arrive before you left. You would violate causality itself. Physicists have analyzed this in detail. Any faster-than-light signal or travel method can be converted into a time machine using known physics. You simply send the message or traveler on a round trip involving motion at high subluminal velocities. The round-trip trajectory, combined with the faster-than-light segment, creates what physicists call a closed time-like curve. You can send information back to your own past. You can, in principle, create paradoxes where you prevent your own message from being sent. Some physicists believe the universe must contain a mechanism that prevents this. Others believe that the absence of evidence for closed time-like curves is itself evidence that they are impossible. Either way, the light cone structure seems to be fundamental. The prison walls are not arbitrary. They are the boundaries of causality itself. What would physics look like without this constraint? Imagine a universe where C was infinite. Causality would propagate instantaneously. Any event could immediately influence any other event, regardless of distance. The universe would have no causal structure at all. Everything would happen simultaneously, in a strange, eternal now. Could life exist in such a universe? It seems unlikely. Life depends on processes, on sequences of events, on cause preceding effect. Without the light cone structure, there would be no sequence, no process, no time in any meaningful sense. Or imagine a universe where C was much smaller, say 100 meters per second, roughly the speed of a fast car. Now, causality is extremely slow. The sun's gravitational influence would take years to reach Earth. Chemical reactions that depend on electromagnetic forces would proceed millions of times slower. The timescales for any complex process would become astronomical. Such a universe might contain life, but it would be unimaginably slow life. Evolution that takes billions of years in our universe would take quadrillions in theirs. Their civilizations, if they arose, would develop over timescales we cannot fathom. Our C, approximately 3 times 10 to the 8th meters per second, seems tuned for complexity. Fast enough for stars to form and chemistry to proceed on manageable timescales. Slow enough to give the universe causal structure and prevent paradoxes. Is this fine-tuning? Is it evidence of design? Or is it simply survivor bias? We exist in a universe compatible with our existence, so naturally, we observe such a universe. These are questions physics cannot answer. What physics tells us is that whatever the reason, C is what it is, and we cannot change it. Let us now examine what happens near the boundary in more detail. Particle accelerators routinely push particles to velocities exceeding 99% of c. The Large Hadron Collider at CERN accelerates protons to 99.999991% of the speed of light. At this velocity, gamma is approximately 7,460. The protons complete 11,245 circuits of the 27-kilometer ring every second. Their clocks run over 7,000 times slower than ours. From the proton's perspective, if such a concept is meaningful, the ring has contracted to about 4 meters in length. These are not hypothetical effects. They are measured routinely. The LHC's design depends on accurate relativistic calculations. If special relativity were even slightly wrong, the accelerator would not function. Cosmic rays provide even more extreme examples. Ultra-high-energy cosmic rays are particles, mostly protons and atomic nuclei, that rain down on Earth from space with extraordinary energies. The most energetic ever detected, the so-called "oh my God" particle, observed in 1991, had energy of about 3 times 10 to the 20th electron volts. This corresponds to a Lorentz factor of over 3 times 10 to the 11. The particle was traveling so close to c that the difference is about 1 part in 10 to the 23. In the reference frame of this particle, if it were intelligent, the entire Milky Way galaxy would be contracted to about 1 centimeter in thickness. Even at this absurd extreme, the particle was still traveling slower than light. No matter how much energy you pump into a particle, no matter how much you accelerate it, you can only get closer to c. Never reach it, never exceed it. This brings us to one of the most profound implications of special relativity, the relativity of simultaneity. In everyday experience, we assume that simultaneity is absolute. If 2 events happen at the same time for you, they happen at the same time for everyone. But this is wrong. Consider 2 lightning strikes that hit the front and back of a moving train at the same moment, as measured by an observer on the ground. For a passenger on the train, these strikes are not simultaneous. The front strike happens first because the passenger is moving toward where it occurred and away from where the back strike occurred. This is not an illusion or a measurement error. The passenger and the ground observer disagree about the fundamental structure of reality, about what happened when. And both are correct within their reference frames. Now extend this to cosmic scales. Consider a galaxy 2 million light-years away. What is happening there right now? The question has no answer. Simultaneity is not defined over such distances. Depending on your velocity, different events in that galaxy count as simultaneous with your present moment. There is no objective now spanning the cosmos. This means something profound for our hopes of cosmic connection. Even if we could somehow communicate instantaneously, we would not know what now to connect to. The concept of, quote, one across astronomical distances is fundamentally undefined. We are not just separated by distance, we are separated by the lack of a common time. The universe has no shared moment that all observers can agree upon. This might seem like abstract philosophy, but it has concrete consequences. Consider the fantasy of instantaneous communication. Many science fiction stories imagine Ansible devices or subspace radios that allow real-time conversation across light years. But such devices would violate causality. If Alice on Earth could send a message to Bob in Andromeda instantly, and Bob could reply instantly, Then from certain reference frames, Bob's reply would arrive before Alice sent her message. The conversation would happen backward in time. This is not speculation. It is a mathematical consequence of relativity. Any faster-than-light communication method creates causal paradoxes when combined with the relativity of simultaneity. The universe does not permit real-time conversation across interstellar distances. Even if civilizations could exchange information, they would be limited to exchanges of monologues, messages sent out and answered generations later. Our isolation is not just spatial, it is causal. It is woven into the deepest structure of space-time. Let us step back and summarize the mathematical situation. The Lorentz transformations describe how space and time coordinates change between reference frames. They preserve the speed of light. They ensure that the light cone structure is invariant. They make faster-than-light travel and communication impossible. These transformations are not arbitrary. They are the unique transformations compatible with the postulates of special relativity. Any modification that allowed FTL would either break Lorentz invariance, introducing a preferred reference frame, or create causal paradoxes. In over a century of testing, Lorentz invariance has been confirmed to extraordinary precision. Experiments with atomic clocks, particle accelerators, GPS satellites, and astronomical observations all agree. The speed of light is constant to at least 1 part in 10 to the 18th. The prism is real. The mathematics is airtight. There are no known loopholes. But mathematics cannot tell us how to feel about our situation. That is a question for philosophy. Some find despair in these equations. They see an infinite universe forever beyond reach, a cosmos of beauty we can observe but never touch. They mourn the interstellar civilizations we will never join, the alien perspectives we will never share. Others find peace. They see the same equations as a structure that makes existence possible, that gives time its direction and causality its meaning. They accept the universe as it is rather than as they wish it were. And some find wonder. The same mathematics that confines us also reveals the astonishing nature of reality. Time is flexible. Space is malleable. The universe has a geometry stranger and more beautiful than human imagination ever conceived. All these responses are valid. The mathematics does not dictate how to feel about it. It merely tells us what is true. In the next part, we will explore the cosmic consequences of our confinement. We will examine the expanding universe and the horizon that separates us from most of reality. We will consider the fate of information and the ultimate limits on what can be known. But for now, sit with the equations. Let the Lorentz factor sink into your understanding. Feel the weight of gamma as it approaches infinity. This is not science fiction. This is the architecture of your cage. And yet, you are still here, still thinking, still wondering about what lies beyond. The prison walls cannot contain your curiosity, even if they contain your body. That, perhaps, is humanity's greatest achievement. We are prisoners who refuse to stop dreaming of freedom. Part 3. The Expanding Prison. Here is something that will fundamentally alter how you perceive your place in the cosmos. The prison is not static, it is shrinking. In 1929, American astronomer Edwin Hubble was working at the Mount Wilson Observatory in California. He had spent years measuring the distances to galaxies using a revolutionary technique involving Cepheid variable stars. These are stars that pulse with a regular period, and the period is directly related to their intrinsic brightness. By comparing intrinsic brightness to apparent brightness, Hubble could calculate distances, and by analyzing the spectra of these galaxies, he could measure their velocities through the Doppler effect. Light from objects moving away from us shifts toward the red end of the spectrum, just as the pitch of an ambulance siren drops as it speeds away. What Hubble discovered shocked the scientific world. Almost every galaxy he measured was moving away from us, and the farther away a galaxy was, the faster it receded. This was not random motion. It was a systematic pattern. The universe was expanding. Let us be clear about what expansion means. The galaxies are not flying through space like shrapnel from an explosion. Space itself is stretching. The fabric of the cosmos is growing, and everything embedded in it moves apart as a consequence. Imagine dots on the surface of a balloon. As you inflate the balloon, the dots move away from each other. No dot is at the center. From any dot's perspective, all other dots are receding. This is roughly what cosmic expansion looks like, though in 3 dimensions rather than 2. Hubble measured the rate of this expansion. He found that a galaxy 1 megaparsec away, about 3.26 million light-years, recedes at roughly 500 kilometers per second. A galaxy 2 megaparsecs away recedes at 1,000 kilometers per second, and so on. This relationship is now called Hubble's law. The current best measurement of the Hubble constant is approximately 70 kilometers per second per megaparsec. This means that for every megaparsec of distance, the recession velocity increases by 70 kilometers per second. Now here is where the prison walls begin to close in. If recession velocity increases with distance, there must be some distance at which it equals the speed of light. Beyond that distance, galaxies recede faster than light. Wait, did I not just explain that nothing can travel faster than light? How can galaxies move at superluminal velocities? The answer is subtle but crucial. The speed limit applies to motion through space. It does not apply to the expansion of space itself. Galaxies beyond a certain distance are not moving through space faster than light. They are stationary in their local space, but that space is being carried away from us faster than light can compensate. This creates a cosmic event horizon, a boundary beyond which we can never receive information, no matter how long we wait. The distance to this horizon is currently about 16 billion light-years. Any galaxy beyond this distance is receding faster than c. Light emitted from such galaxies today will never reach us. They are causally disconnected from our future. But wait. The observable universe has a radius of about 46 billion light-years. How can we see objects beyond the event horizon? The answer involves the universe's history. The expansion rate has changed over time. Galaxies that are now beyond the horizon were once closer. Light they emitted billions of years ago, when they were within the horizon, is still traveling toward us and eventually arrives. We see their ancient images, frozen in time. But we will never see those galaxies as they are today. Their current state is forever unknown to us. And as cosmic expansion continues, we see less and less of their history before they vanish beyond the horizon entirely. It gets worse. The expansion of the universe is accelerating. In 1998, 2 teams of astronomers, the Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees, made an astonishing discovery. They were measuring the distances to Type 1, a supernovae, stellar explosions of remarkably consistent brightness that serve as cosmic standard candles. The data showed something impossible. Distant supernovae were fainter than expected. The universe was not just expanding, it was expanding faster and faster. This acceleration implies the existence of something pushing the universe apart, something with negative pressure that acts as a kind of anti-gravity on cosmic scales. We call it dark energy, though we have no idea what it actually is. It constitutes approximately 68% of the total energy content of the universe. Yet its nature remains one of the deepest mysteries in physics. For their discovery, Perlmutter, Schmidt, and Rees were awarded the Nobel Prize in Physics in 2011. What does accelerating expansion mean for our cosmic prison? It means the walls are closing in at an increasing rate. The event horizon is shrinking. Galaxies that are currently visible will eventually cross it and vanish. The cosmic inventory accessible to us will steadily decrease. In approximately 100 billion years, give or take, observers in our galaxy will see nothing beyond the merged remnant of the local group, the collection of a few dozen galaxies gravitationally bound to the Milky Way. Everything else will have redshifted beyond detection and crossed the event horizon. Future astronomers, if they exist, will look out at an empty universe. They will have no way of knowing that other galaxies ever existed. The cosmic microwave background, the afterglow of the Big Bang, will have redshifted beyond any instrument's ability to detect. The evidence for cosmic expansion will have disappeared. They will conclude, reasonably but incorrectly, that the universe consists of one galaxy in an infinite void. The true nature of the cosmos will be unknowable. We are lucky to exist now, in the cosmic sense. We live in an era when the universe still shows us its structure, when we can still see the evidence of the Big Bang and the expansion that followed. Future generations will be epistemically impoverished in ways we can barely imagine. Let us calculate more precisely what this means for our aspirations. The Andromeda Galaxy, 2.5 million light-years away, is one of the few galaxies approaching us. It is gravitationally bound to the Milky Way and will collide with us in approximately 4.5 billion years. This collision will be spectacular, but not catastrophic. Stars are so widely spaced that actual stellar collisions will be rare. The two galaxies will merge into a single elliptical structure, sometimes called Milkomeda. This merged galaxy, along with the rest of the local group, is our permanent home. We are gravitationally bound to these few dozen galaxies. We will never leave them, not because we lack the will or the technology, but because the universe will not permit it. Every other galaxy in the cosmos is receding. Some are receding slowly enough that, in principle, we could catch them with a sufficiently fast spacecraft launched soon enough. But most are already beyond reach. And as the eons pass, more and more will cross the threshold. The Virgo cluster, the nearest large cluster of galaxies, at about 54 million light-years, is receding at approximately 1,100 kilometers per second. This is only about 0.4% of light speed, so in principle, a relativistic spacecraft could reach it. But consider the journey. At 1% of light speed, which is enormously faster than any spacecraft we have ever built, the journey would take 5.4 billion years. By the time you arrived, the Sun would be a white dwarf. Human civilization on Earth would be ancient history. And Virgo itself is not gravitationally bound to us. It is being carried away by cosmic expansion. By the time your descendants arrived, Virgo would be even farther from their home than when they departed. The universe would have expanded around them during the journey. At 99% of light speed, with severe time dilation, the passengers might experience only about 70 million years. But Earth would still age 5.4 billion years. The round trip would span 10 billion years or more. The Virgo cluster is reachable in theory, unreachable in practice, and it is among the closest large structures. The rest of the universe is already gone. Have you ever looked at images from the Hubble Space Telescope or the James Webb Space Telescope and marveled at the countless galaxies scattered across the frame? Those deep-field images show thousands of galaxies in a patch of sky smaller than a grain of sand held at arm's length. Each of those galaxies contains hundreds of billions of stars. Each star potentially hosts planets. The sheer number of worlds implied is beyond human comprehension, and almost all of them are beyond our reach. Not just difficult to reach, not just expensive to reach, fundamentally, physically, causally inaccessible. The light from those galaxies is ancient. We see them as they were billions of years ago. Their current state is unknown and unknowable. Any civilizations that evolved there have had billions of years to develop, but we will never contact them, never know they existed, never share in their discoveries. The universe is teeming with structure we can observe but never touch. It is a gallery we can only view through windows that are slowly closing. This brings us to a profound question. What is the point of a universe so large if most of it is inaccessible? One answer is that there is no point. The universe simply is what it is. It was not designed for human convenience. It obeys mathematical laws that happen to produce this particular structure, and our feelings about it are irrelevant. Another answer is anthropic. Perhaps the universe must be this large to contain observers. Smaller universes might not have enough time or space for galaxy formation, stellar nucleosynthesis, and the evolution of complex life. We exist in a vast cosmos, because only vast cosmoses can produce beings who wonder why the cosmos is so vast. A third answer is speculative but fascinating. Perhaps the inaccessible regions serve a purpose we do not understand. Perhaps they are not truly separate from us in some deeper sense. Quantum mechanics hints at connections that transcend classical notions of locality. We do not yet have a full theory of quantum gravity, and when we do, our understanding of cosmic structure may change dramatically. But whatever the ultimate answer, the practical situation remains. We are confined. The prison is vast, containing perhaps 1 trillion galaxies we will never reach. And it is shrinking, closing around us at an accelerating rate. Let me describe what this feels like in human terms. Imagine you are in a library containing every book ever written and every book that ever will be written. You can see the shelves stretching away in every direction, filled with knowledge and stories and wisdom beyond measure. But you are confined to a small reading room. You can see through the glass walls into the greater library, but you cannot enter. And every year, the glass walls move inward a little. The visible shelves become fewer. Books that were once at least visible are carried away into darkness. Eventually, your reading room contains only the few books you started with. The rest of the library still exists, but it might as well not. You will never know what is in those distant books. This is our cosmic situation. The local group is our reading room. The rest of the universe is the library, and the walls are closing in. Is there any hope? In the strictest physical sense, no. The speed of light is absolute. Cosmic expansion is accelerating. The event horizon is real. These are not engineering problems to be solved, but fundamental features of reality. But hope is a human concept, not a physical one. Within our reading room, there is more than enough to explore. The Milky Way alone contains between 100 billion and 400 billion stars. The local group adds perhaps 1 trillion more. Even at the glacial pace of sublight colonization, even taking millions of years to spread through our gravitationally bound neighborhood, we would never exhaust the possibilities. And there is the vertical dimension of understanding. We can study the universe we can see. We can analyze the light from distant galaxies before they vanish. We can build theories that describe the cosmos beyond our horizon. We can know, even if we cannot visit. Perhaps true wisdom lies in accepting what we cannot change and embracing what we have. The universe has given us a room in an infinite library. We can rage against the walls, or we can read the books available to us. The choice is ours. Part 4. What physics does not tell us. We've examined special relativity, the Lorentz transformations, the expanding universe, and the cosmic event horizon. The mathematics is rigorous, the observations are precise, the conclusions seem inescapable. And yet, there are things physicists rarely discuss in public. Gaps in our knowledge so profound that they might, just might, contain loopholes we have not yet discovered. Let me be clear. I am not promising escape routes. I am not offering false hope. But intellectual honesty requires acknowledging what we do not know, alongside what we do. Here is the first uncomfortable truth. We do not understand why the speed of light has the value it does. The speed of light, c, is approximately 299,792,458 meters per second. We can measure this to extraordinary precision. We can show that it is constant across all experiments. We can derive relativistic mechanics from its constancy. But we cannot explain why it is this number and not some other number. We cannot derive c from first principles. It is a fundamental constant, meaning it must be measured rather than calculated. This is unsatisfying. A truly complete theory of physics should explain why the fundamental constants have the values they do. If C could, in principle, be different, what determines its value in our universe? Some physicists believe the answer lies in deeper structure. String theory, for example, suggests that the apparent constants of nature arise from the geometry of extra dimensions. If the compactified dimensions have particular shapes and sizes, this fixes the values of coupling constants, masses, and speeds. But string theory has not yet made testable predictions about these values. We do not know if it is correct, let alone whether it truly explains C. The value of the speed of light might be a clue to physics we do not yet understand, and that unknown physics might contain surprises. The second uncomfortable truth concerns dark energy. We know that dark energy exists because we observe its effects. It accelerates the cosmic expansion. It constitutes the majority of the universe's energy content. It has negative pressure and positive energy density. But we have no idea what it actually is. The leading candidate is the cosmological constant, a term Einstein introduced into his field equations and later called his greatest blunder. If the cosmological constant represents the energy of the vacuum itself, quantum field theory predicts its value should be enormous, roughly 120 orders of magnitude larger than observed. This is the worst prediction in the history of physics. Something is deeply wrong with our understanding. Alternatively, dark energy might be a new field, sometimes called quintessence, that evolves over time. It might be modified gravity on cosmic scales. It might be an artifact of inhomogeneous universe models that we are misinterpreting. If we do not understand what dark energy is, we cannot be certain how it will behave in the future. Our predictions of an accelerating expansion assume the cosmological constant remains constant. But if dark energy evolves, the future could be very different. Some models predict that dark energy will eventually reverse, causing the expansion to slow and perhaps reverse into a big crunch. Others predict that dark energy will increase without limit, causing a big rip in which atoms themselves are torn apart. We simply do not know. The acceleration we observe today might not continue forever. The prison walls might stop closing or even begin to open. This is not a prediction. It is an acknowledgement of ignorance. The third uncomfortable truth is that we do not have a theory of quantum gravity. General relativity describes gravity as the curvature of space-time. It works beautifully on cosmic scales, predicting black holes, gravitational waves, and the expansion of the universe. But it is a classical theory. It does not incorporate quantum mechanics. Quantum mechanics describes the behavior of matter and energy at atomic scales. It is spectacularly successful, explaining chemistry, electronics, and the structure of matter. But it treats spacetime as a fixed background, not as a dynamical entity. When we try to combine these two theories, disaster strikes. The mathematics produces infinities that cannot be removed. The predictions become meaningless. Gravity refuses to play nicely with quantum rules. This means we do not understand physics at extreme scales where both gravity and quantum effects are important. The interior of black holes. The first instance after the Big Bang. Perhaps the true nature of spacetime itself. The speed of light is a classical concept. It is the speed at which massless particles propagate through smooth, continuous spacetime. But if spacetime is actually discrete at the Planck scale, if it has a quantum structure we do not yet understand, the very concept of a maximum speed might need revision. I am not saying the light speed barrier will fall. I am saying we are not certain it is as fundamental as we believe. The fourth uncomfortable truth involves the nature of time. In special relativity, time is relative. Different observers measure different durations. But time still flows, still orders events into before and after. In general relativity, the picture becomes more complex. Near massive objects, time runs slower. Inside black holes, the roles of space and time can interchange. Closed time-like curves, loops in spacetime that allow travel to one's own past, are mathematical solutions to Einstein's equations, though they may be forbidden by other principles. But what is time fundamentally? Why does it seem to flow in one direction when the underlying equations of physics are time-symmetric? Why do we remember the past but not the future? These questions do not have satisfying answers. The nature of time remains one of the deepest mysteries in physics, and our understanding of cosmic speed limits depends on our understanding of time. If time is not what we think it is, if it emerges from some more fundamental structure, then the constraints we derive from it might be artifacts of our limited perspective. The fifth uncomfortable truth is that experiments sometimes produce anomalies. In September of 2011, the OPERA experiment at Gran Sasso Laboratory in Italy announced that they had measured neutrinos traveling faster than light. The neutrinos, produced at CERN and detected 730 kilometers away, seemed to arrive 60 nanoseconds earlier than light would. The physics community was skeptical but intrigued. If true, this would overturn a century of relativity. Papers were published exploring the implications. Some physicists suggested Lorentz invariance might be violated at high energies. In February of 2012, the collaboration announced that they had found two errors. A loose fiber optic cable had caused timing problems. An oscillator had been running too fast. When corrected, the neutrino speeds were consistent with light speed. The anomaly was explained. Relativity survived. But here is what troubles some physicists. For several months, a major international collaboration believed they had evidence against one of physics' most fundamental principles. This suggests that our confidence, however justified, rests on foundations that can be tested and, in principle, overturned. Science is not dogma. Every principle, no matter how well established, is subject to revision in light of new evidence. The speed of light has passed every test so far, but the tests continue, and we cannot know for certain what future experiments might reveal. Let me be clear about what I am and am not saying. I am not saying the speed of light is wrong. The evidence for special relativity is overwhelming. Every experiment confirms it. Every technology based on it works. There is no credible alternative. I am saying that physics is incomplete. We have profound gaps in our understanding of dark energy, quantum gravity, and the nature of time. These gaps might contain nothing relevant to interstellar travel, or they might contain surprises. Anyone who claims certainty about what future physics will reveal is overstepping. We do not know what we do not know. The history of science is filled with confident pronouncements that were later overturned. The speed of light barrier might be absolute and eternal, or it might be a low-energy approximation to something more complex. We cannot be certain either way. What we can be certain of is our current situation. With current physics, escape is impossible. We are confined to our local cosmic neighborhood. The universe beyond is and will remain forever out of reach. If you are hoping for a breakthrough that will change everything, you may wait forever. Or you may witness the greatest revolution in the history of physics. There is no way to know in advance. This uncertainty should not be paralyzing. It should be motivating. The gaps in our knowledge are not embarrassments to be hidden. They are frontiers to be explored. The unsolved problems of physics are invitations to future generations of thinkers. Perhaps some young person watching this video will someday contribute to our understanding of quantum gravity. Perhaps the solution will reveal new possibilities we cannot currently imagine. Or perhaps it will confirm that the light speed barrier is indeed fundamental and inviolable. Either outcome would be a triumph of human understanding. Either way, we would know more about our cosmic prison, and knowledge, even knowledge of our limitations, is a form of freedom. Part 5. The Search for Others. If we are imprisoned, we are not necessarily alone in our prison. The Milky Way galaxy contains between 100 billion and 400 billion stars. Current estimates suggest that roughly 1 in 5 Sun-like stars has an Earth-sized planet in its habitable zone. That implies billions of potentially habitable worlds in our galaxy alone. The Drake equation, formulated by astronomer Frank Drake in 1961, attempts to estimate the number of active, communicative civilizations in the Milky Way. It multiplies together factors like the rate of star formation, the fraction of stars with planets, the fraction of planets where life develops, and the fraction of life that becomes intelligent and communicative. The problem is that we do not know most of these factors. Estimates range from a handful of civilizations to millions. The uncertainty is enormous. But here is what we do know. If intelligent civilizations exist elsewhere in the galaxy, they face the same light-speed barrier we do. They cannot reach us quickly, any more than we can reach them. Whatever communication or contact might occur would be separated by centuries or millennia of transmission time. And yet, we search. The search for extraterrestrial intelligence, or SETI, has been ongoing since 1960. Using radio telescopes and, more recently, optical telescopes, scientists scan the sky for signals that might indicate technological activity. So far, nothing definitive has been found. There have been tantalizing anomalies, like the famous WOW signal detected in 1977, but none that have been confirmed as extraterrestrial in origin. This silence is itself informative. If the galaxy were teeming with civilizations broadcasting powerful signals, we would likely have detected something by now. The absence of evidence, while not evidence of absence, suggests that communicative civilizations are either rare, short-lived, or not broadcasting in ways we can detect. The light-speed barrier offers one explanation. Perhaps civilizations arise, look at the distances involved, and conclude that interstellar communication is pointless. Why broadcast if the nearest potential recipient is hundreds of light-years away and will not respond for centuries? Or perhaps civilizations that survive long enough become introspective, turning their attention inward rather than outward. Perhaps they build simulated universes more interesting than the physical cosmos. Perhaps they transcend in ways that make radio broadcasting seem as primitive to them as smoke signals seem to us. We do not know. The silence continues. But consider what contact would mean, even across the light-speed barrier. Imagine we detect an unambiguous signal from a civilization around a star 100 light-years away. The signal is clearly artificial, perhaps containing mathematical patterns or encoded information. We could not have a conversation. Any message we send would take 100 years to arrive, and their reply would take another 100 years to reach us. A single exchange of greetings would span 2 centuries. But we would know we are not alone. The philosophical impact would be immense. And over centuries, meaningful exchange could occur. We could share knowledge, art, philosophy, science. Not in real-time dialogue, but in the slow accumulation of transmitted wisdom. Libraries exchanged between the stars. Each civilization would be enriched by the other's perspective. We would gain insights into alternative paths of evolution, alternative solutions to universal problems, alternative ways of being intelligent. The light-speed barrier would prevent us from meeting in person, but it would not prevent us from knowing each other in a deep and meaningful sense across the vast distances. There is another possibility, one that is harder to discuss but important to consider. What if intelligence, wherever it arises, eventually creates artificial minds that care nothing about the passage of time? A biological being experiences decades as a lifetime. A machine intelligence could experience millions of years as easily. It could board a spacecraft, travel at a few % of light speed, and arrive at a destination in what feels, to it, like no time at all. Such beings might already be crossing the galaxy at sublight speeds. They would have had billions of years to spread if the first civilizations arose early in cosmic history. Their probe networks might already be in our solar system, watching, waiting, or simply passing through on journeys we cannot comprehend. This is the basis for the concept of von Neumann probes, self-replicating machines that could colonize a galaxy in a few million years, even at modest velocities. If any civilization ever built such probes, the galaxy should be filled with them by now. The fact that we do not observe such probes is itself a puzzle. Perhaps they do not exist. Perhaps they are here, but undetectable. Perhaps they have been and gone, leaving no trace we can find. Perhaps some filter prevents civilizations from reaching the technological level required to build them. The light-speed barrier does not prevent the spread of machine intelligence through the galaxy. It merely slows it down. And on cosmic timescales, millions of years is a blink. Let us return to the personal level. You are watching this video on a small planet orbiting an ordinary star in the suburbs of an unremarkable galaxy. The light from the nearest star beyond the Sun has been traveling for 4 years to reach your eyes. The light from the nearest large galaxy has been traveling for 2.5 million years. You are surrounded by immensity you cannot visit. You are embedded in a cosmos so vast that even light, the fastest thing in the universe, crawls across it for billions of years. And yet, you are here. You are thinking about these things. You are processing information at a rate far exceeding anything else in your corner of the cosmos. The atoms in your body were forged in stellar cores and scattered across space by supernova explosions. You are literally made of star stuff, as Carl Sagan famously observed. The universe has spent billions of years constructing the matter that now contemplates its own existence. Is that not remarkable? Does that not deserve wonder, regardless of what lies beyond our reach? Part 6. Finding meaning in confinement. We have traveled far in this exploration. We have seen the mathematics of our prison, the expanding walls, the gaps in our knowledge, and the search for cosmic companions. Now, we must address the most personal question of all. How do we live with this knowledge? How do we find meaning in a universe that offers so much, but withholds so much more? Different people will answer differently, and all answers deserve respect. But let me offer some thoughts. First, we must distinguish between what we can observe and what we can affect. We can observe the entire observable universe. We can study galaxies billions of light years away. We can analyze the cosmic microwave background and reconstruct conditions moments after the Big Bang. Our knowledge can extend far beyond our physical reach. This is not a small thing. The human mind has managed to comprehend scales that dwarf everything we directly experience. We understand nuclear physics and cosmic structure. We can predict eclipses and calculate orbital mechanics. We have mapped the observable universe in exquisite detail. The light-speed barrier limits what we can touch. It does not limit what we can know. And for creatures whose primary gift is understanding, this distinction matters. Second, we must recalibrate our sense of scale. We tend to think of our confinement as tragic because we compare it to the infinite universe. But compare it instead to what we actually have. The Earth has a surface area of roughly 510 million square kilometers. Humans have explored and inhabited only a fraction of this. There are depths of our oceans we have never visited, species we have never catalogued, ecosystems we barely understand. The solar system is even vaster. The Moon, Mars, the asteroid belt, the moons of Jupiter and Saturn, the Kuiper belt, the Oort cloud. Enough real estate for trillions of human beings. Enough resources for civilizations lasting billions of years. And the local group, our gravitationally bound neighborhood, contains over 50 galaxies. Most are small, but the Milky Way and Andromeda together contain hundreds of billions of stars. We speak of being confined as if we were in a prison cell, but our cell is larger than we can possibly exhaust. Our confinement is relative to infinity, not to any meaningful human scale. Third, we must consider the role of time. The universe is approximately 13.8 billion years old. Human civilization is roughly 10,000 years old. We have existed for less than 1/1,000,000th of cosmic history. And yet, we have already developed physics sophisticated enough to understand our situation. We have built telescopes that see to the edge of the observable universe. We have sent probes beyond the solar system. What might we accomplish in another 10,000 years, another million years, another billion years? The solar system will remain habitable for hundreds of millions of years. Our descendants, whether biological or mechanical, have timescales available to them that dwarf all human history. What they will achieve is beyond our imagination. Perhaps they will develop technologies that seem magical to us today. Perhaps they will expand to fill the local group. Perhaps they will find ways around limitations that seem insurmountable to us. Or perhaps they will simply accept their situation and build lives of meaning within it. Either outcome is worthy of our hopes. Fourth, we must recognize that meaning is not found only in exploration. Western culture, particularly American culture, valorizes expansion. More territory, more resources, more growth. We instinctively equate progress with spreading outward. But other cultures have found meaning in depth rather than breadth, in contemplation rather than conquest, in understanding rather than domination. Perhaps the universe is structured to encourage such an inward turn. Perhaps civilizations that survive long enough eventually realize that the true frontier is not physical space, but inner experience. Perhaps the light-speed barrier is a cosmic invitation to explore consciousness rather than collect stars. This may sound like rationalization, but consider the alternative. If every civilization eventually encounters the light-speed barrier and finds it impassable, then every mature civilization must make peace with confinement. The alternative is eternal frustration, which is unlikely to lead to flourishing. The universe may be teaching us something. Whether we learn the lesson is up to us. Fifth, we must hold our conclusions humbly. Everything I have said is based on current physics and current understanding. Both are incomplete. Future generations may look back on our certainties with amusement, as we look back on the certainties of past centuries. Perhaps the speed of light is truly absolute and will never be circumvented. Or perhaps there are aspects of physics we do not yet understand that will change everything. Either way, wisdom lies in accepting uncertainty. We do not know what future science will reveal. We do not know what future technologies will enable. We do not know what future intelligences will understand. All we can do is live with integrity in the present, advancing knowledge as best we can and leaving the future to those who will inhabit it. Part 7. The View from Beyond. Let us end with a thought experiment. Imagine you could step outside the universe entirely and view it from some impossible external vantage point. What would you see? You would see a four-dimensional structure, space-time extending from a singular beginning through an expansion that continues to this day. You would see the light cones branching outward from every event, defining the causal structure of reality. You would see matter clustering into stars and galaxies, consciousness emerging on scattered worlds, minds contemplating their own existence. From this vantage point, the light-speed barrier would not seem like a prison. It would be the connective tissue of reality, the structure that makes causality possible, the framework within which physics operates. You would see that the barrier is not arbitrary, it is necessary. Without it, there would be no space-time. Without space-time, there would be no physics. Without physics, there would be no stars, no planets, no life, no minds. The prison is the price of existence. You would also see something humbling. In all that vast expanse, in all those billions of years, conscious beings occupy the smallest fraction of space and time. Most of the universe is vacuum. Most of matter is dark and inert. Most of cosmic history has no witnesses. And yet, the witnesses exist. In scattered pockets, on tiny worlds, minds have arisen that can contemplate the whole. These minds are rare beyond measure. They are precious beyond calculation. You would see that each conscious being is a miracle, a pattern of matter so complex and so improbable that it defies comprehension. The universe has labored for billions of years to produce these patterns. They are its crowning achievement, however brief and localized. From this perspective, the question is not why we are confined, but how we exist at all. Let me bring this back to you, specifically. You are made of atoms that were present at the Big Bang. You carry within you the residue of the first moments of cosmic history. The protons in your body are 13.8 billion years old. Those atoms have been through countless transformations. They were compressed in stellar cores and scattered by supernova explosions. They drifted through interstellar space for millions of years. They coalesced into a planet, organized into complex molecules, and eventually became part of a living organism that can read and understand this sentence. The journey from the Big Bang to your consciousness is the most remarkable story in the universe, and you are its current endpoint. The speed of light is not your enemy. It is the constant that made your existence possible. It is the rate at which the universe constructed itself, the pace at which causality built complexity, the tempo of cosmic evolution. You are not imprisoned by the speed of light. You are created by it. What, then, should we take from all of this? The speed of light is a prison. This is factually true. We cannot escape it. We will never travel freely among the stars. The universe will remain mostly beyond our reach. But the prison contains everything that matters to us: our planet, our solar system, our galaxy, our local group. Enough space for any civilization. Enough time for any ambition that operates on finite timescales. And the prison has windows. We can see out, even if we cannot travel out. We can study the cosmos in exquisite detail. We can know the universe, even the parts we cannot visit. The meaning we make is not diminished by the distances we cannot cross. Love, beauty, understanding, connection, these are not measured in light years. They occur right here, right now, in the tiny fraction of the cosmos we call home. The universe is vast and cold and mostly empty. It does not care about us. It is not designed for our comfort or our ambitions. But we can care about it. We can study it, appreciate it, wonder at it. We can find meaning in a cosmos that offers none. We can create significance in a universe of indifferent physics. This is the human achievement. Not escaping our constraints, but thriving within them. Not conquering the cosmos, but understanding our place in it. Not raging against the prison walls, but appreciating the vast and beautiful space they contain. The speed of light is 299,792,458 meters per second. It will not change. It cannot be negotiated with. It is the architecture of reality itself. And within that architecture, you exist. You think. You feel. You wonder. Is that not enough? Look up at the night sky. The stars you see are real. The galaxies beyond them are real. The universe stretching to the edge of the observable horizon is real. You cannot reach most of it, but you can see it. You can know it. You can include it in your understanding of what is. The speed of light separates you from infinity, but it also connects you to everything you can see. Every photon reaching your eye has traveled at exactly c, carrying information from across the cosmos directly to your consciousness. You are the universe looking at itself. You are matter contemplating matter. You are the light speed barrier becoming aware of its own existence. And in that awareness, there is freedom. Not freedom from physics, but freedom within physics. The freedom to understand, to appreciate, to find meaning in the face of indifferent vastness. The prison walls will never fall, but the prisoner can still dream, still learn, still love. And perhaps that is what the universe wanted all along. Perhaps the speed of light is not a barrier to meaning, but the very thing that makes meaning possible. Final reflections. I have told you that humanity will never escape the speed of light. I have shown you the mathematics, the cosmology, the profound gaps in our knowledge. I have not offered false hope or easy answers. But I have also shown you something else. The constraints that confine us also create us. The laws that imprison us also enable us. The universe that limits our reach gives us the capacity to reach it all. We are brief patterns in a cosmos of unimaginable scale and duration. We exist for a moment, comprehend a fraction, and then dissolve back into the matter from which we arose. The stars we cannot visit will burn for eons after we are gone. And yet, in this moment, we understand. We see the structure of reality. We grasp the equations that govern everything from quarks to quasars. We know our place in the cosmic order, even if that place is humbling. This knowledge is not nothing. It is, perhaps, everything. The speed of light is a prison, but it is also a gift. It is the rate at which existence unfolds, the tempo of causality, the heartbeat of the cosmos. Without it, there would be no us to feel confined. So here is my final question for you. The universe has given you consciousness. It has given you the capacity to understand your situation. It has given you a small corner of space and time in which to live and love and wonder. What will you do with these gifts? Will you mourn what you cannot have, or celebrate what you do have? Will you rage against the prison walls, or explore the vast space they contain? Will you despair at cosmic distances, or marvel at cosmic structure? The choice is yours. Physics determines what is possible. It does not determine what matters. Look up at the stars tonight. See them for what they are. Lights from ancient nuclear fires, photons that have traveled for years or centuries or millennia to reach your eyes. Each one is a message from the cosmos, a testament to the constancy of light speed, a reminder of both your confinement and your connection. You cannot go there, but they have come to you. The universe has sent ambassadors of light to every point in space, carrying information about its structure and history. You receive these ambassadors every night, whether or not you pause to acknowledge them. The speed of light is a prison, and it is a bridge. It separates you from infinity and connects you to everything you can see. It confines you to a small region of space-time and fills that region with photons from across the cosmos. Humanity will never escape, but humanity will never stop wondering, never stop learning, never stop reaching toward the unreachable. That is who we are. Prisoners who dream of freedom. And in the dreaming, we find something better than escape. We find meaning.